Welcome to Explained in 10 Minutes. Today we'll uncover quantum computing. In this video, we will go step by step through one of the most mysterious yet powerful technologies being developed today. You've probably heard the term quantum computing in the news or on social media, but most explanations feel overly complicated. Today we're going to break it down in simple terms. In just a few minutes, you'll not only understand what quantum computing is, but also why it's such a big deal for science, technology, and the future of humanity. We'll avoid jargon and heavy mathematics, focusing instead on clear examples, stories, and analogies that make sense even if you've never studied physics. So, get ready to enter the strange and fascinating world of quantum mechanics, where reality works very differently from what we experience every day. First, let's start with the basics. What does a computer really do? At its core, a computer is a machine that processes information by following rules step by step. Classical computers, the ones we use every day, process information in small units called bits. Each bit is binary, meaning it can only take two values, 0 or 1, like a light switch that is either off or on. By combining billions of these bits together, computers can perform incredibly complex operations and solve problems we use daily, like running apps or browsing the web. But when problems become too complex, like simulating molecules or solving enormous optimization puzzles, even supercomputers struggle and hit a wall. This is where quantum computing comes in, a completely new way of thinking about information and computation. Instead of using classical bits, quantum computers use quantum bits, also known as qubits. Qubits are governed by the rules of quantum mechanics, the science that explains how particles behave at the atomic and subatomic scale. Unlike bits, qubits can exist as 0, 1, or both at the same time thanks to a phenomenon called superposition. Superposition is like spinning a coin in the air. Until it lands, it's not just heads or tails, but a mixture of both possibilities. Another extraordinary feature of qubits is called entanglement, one of the strangest yet most powerful phenomena in physics. When two qubits are entangled, their states become linked in such a way that changing one instantly affects the other, no matter how far apart they are. Einstein himself called this effect spooky action at a distance, because it defies our everyday understanding of cause and effect. Entanglement allows quantum computers to create powerful connections between qubits, multiplying their computational potential. What are some of the applications of quantum computing? In simple terms, it's like having a secret instant communication channel between particles, allowing complex calculations to unfold far faster than classical methods. Classical computers evaluate possibilities largely one after another, even when parallelized, which becomes painfully slow when the number of possibilities explodes, what computer scientists call combinatorial explosion. Problems like route planning, portfolio optimization, or molecular simulation can scale so quickly that even the fastest supercomputers crawl. This limitation isn't about clock speed, it's about the structure of the problem and how many configurations must be examined. Quantum computers approach these hard problems differently by exploiting superposition and entanglement to explore a structured space of possibilities in a single computational pass. Rather than checking every option individually, quantum algorithms prepare many candidate states at once and use carefully designed operations so that paths leading toward correct answers reinforce, interfere constructively, while wrong paths cancel out, interfere destructively. This doesn't mean they magically try everything. It means they manipulate probability amplitudes to bias outcomes toward good solutions. Imagine a massive maze with countless branches. A classical strategy is to walk each path, mark dead ends, and backtrack, time-consuming as the maze grows. A quantum strategy initializes a wave of possibilities through the maze, then shapes that wave with gates, so that it resonates most strongly along paths that lead to the exit. When you finally measure, the wave collapses, and you are most likely to read out a correct path. The magic is in the tuning of that resonance via the algorithm. Interference is the secret sauce. In everyday life, waves can add or cancel. Quantum algorithms use the same idea, but with complex probability amplitudes. By sequencing quantum gates, an algorithm amplifies amplitudes associated with correct answers and suppresses those for wrong answers. The art of algorithm design, like in Grover's search or Shor's factoring, is figuring out which transformations make the right answers light up and the wrong ones fade away. The result is not a blanket speedup for everything, but dramatic advantages for specific tasks. Some problems gain quadratic speedups, noticeable but not world-shattering, while a few gain exponential speedups that remake what's practically computable. Understanding this nuance is essential. Quantum computing is a powerful specialty tool, not a faster version of your laptop for email, video editing, or gaming. Cryptography is the most famous application. Much of today's secure internet traffic relies on factoring large numbers, RSA, or related hard problems. Shor's algorithm, in theory, can factor those numbers exponentially faster than classical methods, threatening widely used encryption standards. This risk is pushing governments and industry to develop and deploy post-quantum, quantum-resistant cryptography that remains secure even in a quantum era. In medicine and chemistry, quantum computers can natively simulate quantum systems, molecules, and materials, because nature itself is quantum. Classical simulations quickly become intractable as electrons interact in complex ways. Quantum simulation promises accurate predictions of molecular energies, reaction pathways, and material properties, accelerating drug discovery and enabling catalysts for cleaner energy. Finance is rich with optimization problems, allocating capital across assets, hedging risk, or scheduling complex trades under constraints. Quantum optimization methods, exact or hybrid variational approaches, aim to find better portfolios or schedules by exploring many feasible configurations in parallel and converging faster on high-quality solutions. Early demonstrations run on small devices or simulators, but the direction is promising. Climate and material science depend on modeling systems with staggering complexity: turbulent fluids, interacting particles, or crystalline lattices under stress. Quantum-enhanced simulation could refine long-range weather models, improve battery chemistries, design lighter and stronger alloys, and uncover superconductors that operate at higher temperatures, breakthroughs with direct impact on energy and sustainability. Artificial intelligence may also benefit, though the picture is nuanced. Quantum machine learning explores ways to speed up certain linear algebra subroutines, like solving large systems or kernel methods, and to encode data into quantum states for richer feature spaces. While we're far from a quantum replacement for today's deep learning, hybrid pipelines that offload hard subproblems to quantum coprocessors could offer practical advantages as hardware matures. To grasp the difference between classical and quantum approaches, consider this. Certain cryptographic challenges or molecular simulations would take a classical supercomputer billions of years to complete. These aren't just slow, they are practically impossible. That boundary between what is theoretically possible but effectively unreachable is where quantum computing shows its true value. Quantum computers can potentially perform the same calculations in hours or even minutes because they harness superposition and interference to explore solution spaces much more efficiently. What seems like magic is actually a precise exploitation of the probabilistic nature of quantum mechanics. That said, quantum computers won't make your smartphone obsolete or instantly render classical computing irrelevant. They are not general replacements for laptops, PCs, or even high-performance servers. Instead, they are domain-specific accelerators that shine only on certain types of problems. Everyday tasks, streaming video, word processing, web browsing, remain best handled by classical computers, which are already optimized for reliability, speed, and affordability. Quantum processors would add no benefit here. In fact, They are currently far too fragile and specialized. It helps to think of quantum computers as specialized super tools. Just as we don't replace a screwdriver with a particle accelerator, we won't replace a laptop with a quantum chip. Instead, when the problem is right, cryptography, simulation, optimization, a quantum computer will provide breakthroughs beyond any classical method. Despite their limitations, real progress is being made. Around the world, governments, startups, and technology giants are investing billions into building prototypes, refining algorithms, and testing early applications of quantum computing. One milestone came from Google in 2019, when they announced their 53-qubit processor Sycamore had achieved what they called quantum supremacy. This means the device solved a specific problem dramatically faster than the world's best classical supercomputer. The problem Google's machine solved wasn't something with immediate practical value. It involved generating random numbers with a particular distribution. But it demonstrated the core idea. A quantum device can outperform classical machines on certain benchmarks. The announcement sparked debate. Some argued that classical machines could be optimized further, narrowing the gap. Others pointed out that supremacy in one contrived task doesn't mean practical usefulness. But nearly everyone agreed it was a milestone worth noting. What matters most is momentum. The field is advancing from theoretical curiosity to engineering challenge, with companies like IBM publishing roadmaps toward machines with thousands of qubits. Each step brings us closer to practical, real-world use cases for quantum computing. Qubits are extraordinarily delicate. Unlike classical bits, which are stable and reliable, qubits can easily lose their information due to tiny disturbances from heat, electromagnetic noise, or even cosmic rays. This fragility is one of the biggest hurdles in building practical quantum computers. This loss of information is known as decoherence. When qubits decohere, they no longer maintain the delicate superpositions that make quantum computation possible. Maintaining coherence long enough to complete complex calculations is a central challenge in the field. Even small vibrations or slight temperature fluctuations can cause errors in qubits. This is why most experimental quantum computers are housed in ultra-low temperature environments, often just a few thousandths of a degree above absolute zero. These extreme conditions are necessary because thermal energy at higher temperatures disrupts the fragile quantum states. The engineering required to maintain these conditions is a major part of the cost and complexity of quantum hardware. Scaling quantum computers to hundreds or thousands of qubits introduces additional challenges. Each new qubit must be controlled precisely, and errors must be corrected without disturbing other qubits. This makes designing large-scale quantum processors incredibly difficult. To address these issues, scientists are developing quantum error correction techniques. By encoding logical qubits into multiple physical qubits, errors can be detected and corrected, preserving the integrity of calculations. Quantum error correction is resource-intensive. Protecting a single logical qubit may require thousands of physical qubits, which increases the size and complexity of quantum processors dramatically. Despite these difficulties, error-corrected quantum computing remains a central goal because it promises reliable, scalable quantum machines capable of solving meaningful problems that classical computers cannot. Researchers are also exploring hybrid architectures that combine classical and quantum processing. These systems use quantum devices for specialized calculations, while relying on classical computers for the bulk of data handling and control. Together, error correction and hybrid approaches are paving the way for practical quantum computing, bringing us closer to solving real-world problems in cryptography, chemistry, optimization, and beyond. Looking ahead, the next decade will likely see hybrid quantum classical systems become more common. These systems leverage the strengths of quantum computing for highly specialized tasks while relying on classical computers for conventional processing. Quantum processors will act as coprocessors, accelerating calculations that are intractable for classical computers alone. This synergy allows us to tackle problems like complex molecular simulations, large-scale optimization, and cryptography more efficiently. Industries that can exploit quantum speedups will gain a significant competitive advantage. Pharmaceuticals could discover new drugs faster, logistics companies could optimize routes more efficiently, and financial institutions could improve risk modeling. Hybrid quantum systems may also play a pivotal role in machine learning and artificial intelligence, performing computations that enhance predictive modeling or enable quantum-inspired algorithms for data analysis. Quantum computing will not replace existing technologies, but will complement them. In the same way GPUs accelerated graphics and AI computations without replacing CPUs, quantum processors will tackle problems beyond classical reach. One of the most transformative applications lies in cryptography. Many current encryption methods could be broken by sufficiently large quantum computers, prompting the development of quantum-resistant cryptography to secure communications in the future. Governments and organizations are already investing heavily in post-quantum cryptography standards. This is essential to protect sensitive data before powerful quantum computers become widespread. Quantum computing could also revolutionize chemistry and materials science. By simulating molecular interactions directly on quantum hardware, scientists can predict reaction outcomes and discover new materials with unprecedented efficiency. These advances may lead to breakthroughs in clean energy, such as more efficient batteries, catalysts for sustainable fuel production, or superconducting materials that reduce energy loss. The potential impact on global sustainability is enormous. Ultimately, quantum computing represents a technological leap rather than just an incremental improvement. It opens doors to problem-solving capabilities far beyond classical limits, laying the foundation for a future shaped by unprecedented computational power. Quantum mechanics challenges our understanding of reality itself. Particles can exist in multiple states simultaneously, and their behavior often defies everyday intuition. This strangeness is not a limitation, it's the power that quantum computing exploits. Superposition and entanglement allow quantum computers to explore solution spaces in ways that classical systems simply cannot. What seems weird in daily life is precisely what makes these machines extraordinary for computation. Quantum phenomena also push the boundaries of human imagination. Concepts like particles influencing each other instantaneously across distance or existing in multiple states at once may sound like science fiction, but experiments repeatedly confirm these behaviors. These counterintuitive principles are harnessed through carefully designed quantum algorithms. By orchestrating interference patterns and entangled states, computations that would take millennia classically can be completed in hours or minutes. The philosophical implications are profound. Quantum computing reminds us that reality is far more complex than it appears. It challenges not only technology, but also our perspective on the natural world. Even though quantum computers are unlikely to replace classical machines for everyday tasks, their impact on science, technology, and industry will be monumental. Specialized problems in cryptography, simulation, and optimization will be revolutionized. Progress in quantum computing is gradual but steady. Researchers continue to improve qubit stability, error correction, and algorithm efficiency, moving closer to practical applications that can address real-world challenges. Each milestone, whether it's increasing qubit counts, achieving error-corrected operations, or demonstrating quantum advantage, brings us closer to realizing the full potential of quantum technology. The future of computation will likely be a collaboration between classical and quantum systems, leveraging the strengths of each. This hybrid approach ensures that quantum computing enhances, rather than replaces, existing technologies. In just 10 minutes, you now have a comprehensive understanding of quantum computing, its principles, potential, challenges, and implications. As this technology matures, it promises to reshape industries, accelerate discoveries, and expand the frontiers of human knowledge. Quantum computing uses the strange rules of quantum mechanics to solve problems that are nearly impossible for today's computers. It's still early, but the potential is enormous. If you enjoyed this explanation, don't forget to like, subscribe, and share this video with someone curious about the future of technology. Thanks for watching, and I'll see you in the next episode of Explained in 10 Minutes.